Hello everyone, welcome to today's presentation. I'm excited to have you here. Today we will explore matter in our surroundings. This is our first slide, so I want to briefly introduce the topic. We'll be looking at what matter is, its different states, and how it exists around us in our daily lives. Let's get started and discover the fascinating world of matter together. Let's dive into the physical nature of matter. When we talk about matter, we're referring to anything that has mass and takes up space. This includes everything around us, from the air we breathe to the objects we use daily. Understanding the physical nature of matter helps us grasp how substances behave and interact in our environment. It's the foundation for exploring how matter can change states and undergo various processes. So, as we move forward, keep in mind that matter's physical properties are what allow us to observe and measure these changes easily. This key concept ties everything together in our overall understanding of the material world. So, what exactly is matter? Well, matter is everything around us that has mass and takes up space. It's the stuff that makes up everything we see, touch, and even things we can't see directly. From the air we breathe to the chairs we sit on, all of it is made of matter. Understanding matter is fundamental because it helps us grasp how the universe is structured and how things interact at both the microscopic and macroscopic levels. As we explore further, we'll see how matter behaves and what it's made of, which ties into the bigger picture of how everything in our world is connected. So, what exactly is matter? Well, anything around us that has mass and takes up space is considered matter. For example, the air we breathe, the food we eat, stones, clouds, stars, plants, and animals, even something as small as a drop of water or a tiny grain of sand. Everything you see and touch falls into this category. It's interesting to note that early Indian philosophers had a unique way of classifying matter. They believed that everything could be broken down into 5 basic elements, which they called the Panchtattva. These are air, earth, fire, sky, and water. Understanding what matter is helps us see how everything around us is interconnected, and it sets the foundation for exploring the different forms and states of matter throughout this presentation. Let's explore the physical nature of matter. Matter, as you know, makes up everything around us, from the air we breathe to the objects we see daily. At its core, matter is composed of tiny particles that are too small to see with the naked eye. These particles are constantly in motion, which gives matter its unique properties. Understanding this physical aspect helps explain why matter behaves the way it does, why solids keep their shape, liquids flow, and gases expand to fill their containers. Recognizing the physical nature of matter is fundamental because it connects to how substances interact, change states, and respond to different conditions. This sets the foundation for more complex concepts we'll explore later in the presentation. Matter is made up of tiny particles, and these particles are the fundamental building blocks of everything around us. What's really fascinating is that the particles themselves are extremely small, so small that we can't see them with the naked eye. This tiny scale is what gives matter its physical properties, like volume and mass. Understanding that matter is composed of these minuscule particles helps us grasp how it behaves and interacts on a microscopic level. Remember, this concept is key to understanding the physical nature of matter and how it forms the world we experience every day. Now, let's look at some key characteristics of particles of matter. First, particles are in continuous movement. They are always moving, which means they possess what we call kinetic energy. When the temperature increases, these particles move even faster. So, higher temperature equals higher kinetic energy. This movement is important because it explains many behaviors of matter. For example, diffusion occurs when particles of different types, like sugar or salt, spread out and intermingle on their own. This happens because particles are constantly moving and mixing. Next, there's the space between particles. You might have seen how particles of substances like sugar, salt, dettol, or potassium permanganate evenly distribute in water. They don't just stay in one place, they move into the tiny gaps between other particles. This shows us that there is actually enough space between particles of matter to allow this kind of movement and mixing. Finally, let's talk about the force of attraction. Particles of matter aren't just bouncing around randomly. they also attract each other with a force. This force is what keeps particles close together, forming the structure of different states of matter. The strength of this attraction can vary from one type of matter to another, which helps explain why some substances are solids, others are liquids, and some are gases. All these characteristics, movement, space, and attraction, are fundamental in understanding how matter behaves in our everyday world. Today, we're going to explore the different states and forms of matter. Matter, as you know, is everything around us that has mass and takes up space. The most common states of matter are solid, liquid, and gas, but there are also others like plasma and Bose-Einstein condensates. Let's start with solids. Solids have a fixed shape and volume because their particles are tightly packed together and only vibrate in place. This gives solids their firmness and stability. Moving on to liquids, they have a definite volume but take the shape of their container. Their particles are close but can slide past each other, allowing liquids to flow smoothly. Gases are quite different. They don't have a fixed shape or volume and will expand to fill any space. Their particles are spread out and move freely, which makes gases compressible and adaptable to their containers. There are also some other interesting states like plasma, which is a super hot, ionized state of matter found in stars, and Bose-Einstein condensates, which occur at extremely low temperatures and exhibit unique quantum properties. Understanding these states helps us see how matter behaves under different conditions, which ties into the overall theme of how matter changes and interacts in our universe. Today, let's explore the states and forms of matter. The matter around us exists in 3 different states, which are solid, liquid, and gas. These states arise because of differences in the characteristics of the particles that make up matter. For example, in solids, particles are tightly packed together and have a fixed shape. In liquids, particles are still close but can move around each other, allowing the liquid to flow and take the shape of its container. And in gases, particles are much farther apart and move freely, filling the entire space available. Understanding these states helps us see how matter behaves in different conditions and connects to the overall theme of how matter interacts with its environment. Now let's talk about the properties of solids. If a matter has certain characteristics, then we can classify it as a solid. First, solids have a definite shape. This means they retain their shape without needing a container to hold them in place. Second, they have negligible compressibility, which means you can't easily squeeze or compress them into a smaller volume. They resist being compressed. Third, solids have distinct boundaries and fixed volumes. This means they occupy a specific space, and that space doesn't change easily. Lastly, solids tend to maintain their shape even when you apply an outside force. They are rigid because, although they may break under strong force, it's quite difficult to change their shape. This rigidity is a key property that sets solids apart from liquids and gases. Understanding these properties helps us grasp why solids behave the way they do in different situations and how they fit into the broader study of matter. Let's take a closer look at the properties of liquids. First, they don't have a fixed shape like solids do, but they do have a fixed volume. That means no matter what container you pour them into, they will always occupy the same amount of space. Speaking of containers, liquids take the shape of whatever they're in, so they adapt to different forms easily. Now, the particles inside a liquid move around more freely compared to solids, and there's more space between them. This increased movement and spacing give liquids their fluid nature. Because they can flow and change shape so easily, we describe liquids as being fluid. This flexibility is a key characteristic that sets liquids apart from solids and gases, and it's essential to understanding their behavior in different situations. Let's talk about some key properties of gases. First, gases do not have a fixed shape like solids or liquids do. Instead, they take the shape of the container they are in, but they do have a fixed volume, which is quite interesting. Another important point is that gases are highly compressible. Compared to solids and liquids, you can easily squeeze or compress gases into smaller spaces, which is useful in many practical applications. Now, if we look at the particles of gases, you'll notice they are spread out with large spaces between them. This wide spacing allows gases to diffuse or spread out quickly into their surroundings, which explains why smell, for example, can travel fast through the air. Connecting this to the overall theme, these properties highlight the unique behavior of gases and help us understand how they interact with their environment. Gases are flexible, easy to manipulate, and capable of rapid movement, which makes them fascinating to study. Can matter change its state? Well, this is a fascinating question because it gets right to the heart of what matter is and how it behaves. Essentially, yes, matter can change its state, and this process is all about the energy interactions involved. For example, when we heat ice, it melts and turns into water, and if we keep heating it, it can even turn into steam. Conversely, cooling steam turns it back into water, and further cooling condenses it into ice again. These changes are what we call phase transitions. The most important concept here is that these changes aren't just superficial. They involve the rearrangement of particles and a transfer of energy. This ties into the overall theme of matter's versatility and responsiveness to environmental conditions. Understanding how matter changes states helps us grasp the dynamic nature of the physical world around us. Can matter change its state? Yes, that's right. Variations in temperature and pressure can cause matter to change from one state to another. For example, when you heat ice, it melts into water, and when you increase pressure, gases can become liquids. These changes are fundamental because they demonstrate how matter is not fixed. It can adapt depending on environmental conditions. Understanding these concepts helps us see the dynamic nature of matter and connects to the broader theme of how matter behaves in different situations. It's all about how temperature and pressure play a critical role in transforming matter from one form to another. When we increase the temperature of solids, what's happening at the particle level is quite fascinating. The kinetic energy of the particles rises, meaning they start moving faster and vibrating more vigorously. This extra energy supplied by heat actually helps overcome the attractive forces holding the particles in fixed positions. As a result, the particles begin to leave their original spots and move more freely, which is the process of melting. Now, an important concept to remember here is the melting point. This is the specific minimum temperature at which a solid transforms into a liquid under atmospheric pressure. Understanding this helps us grasp how temperature influences state changes, which is a key part of our overall discussion on matter and thermal energy. Let's take a closer look at the concept of latent heat. The term latent means hidden, and in this context, it refers to heat that is not immediately visible or apparent. When we heat ice, for example, the temperature doesn't rise right away, even though energy is being absorbed. This absorbed energy is actually used to break the forces of attraction between the ice particles. It's like the heat is going into the structure itself, rather than increasing the temperature. That's why we call it latent heat, because it's hidden within the material. Now, an interesting point to remember is that at 0 degrees Celsius, or 273 Kelvin, the particles in water have more energy than the particles in ice at the same temperature. This happens because, during melting, the energy is used to overcome the attractive forces holding the particles together, not to increase their temperature. So, even though the temperature stays constant, the particles are actually gaining energy internally. This concept helps us understand phase changes better, how energy can be absorbed or released without changing the temperature, but instead changing the state of the substance. It's a key part of understanding heat transfer and the energy involved in melting, boiling, and other phase transitions. Now, let's explore sublimation and deposition, which are fascinating changes of state. Sublimation occurs when a solid turns directly into a gas without becoming a liquid first. This is quite interesting because it skips the liquid phase altogether. You might have seen this happen with substances like camphor or naphthalene balls, those mothballs you might have in your closet. They slowly disappear without melting, which is a perfect example of sublimation. On the other hand, deposition is the reverse process. It's when a gas turns directly into a solid without passing through the liquid stage. A common example of this is dry ice or solid carbon dioxide. When dry ice is exposed to warmer temperatures, it turns directly into carbon dioxide gas, skipping the liquid phase completely. Both sublimation and deposition are examples of how matter can change states in ways that aren't always straightforward. They connect to the overall theme of phase changes, showing us how versatile and dynamic matter really is. These processes are not just scientific curiosities. They have practical uses in industries like freeze-drying food or creating special effects in theater and film. Now, let's talk about the effect of pressure change on the state of matter. As you can see, the state of matter really depends on pressure variations. When we increase the pressure, the gas particles are pushed closer together. This crowding causes some interesting changes. For example, a gas can turn into a liquid when the particles are compressed enough. And if we keep increasing the pressure even further, that liquid can become a solid. This demonstrates how pressure plays a crucial role in transforming matter from one state to another. It ties into our overall theme of understanding how different factors influence the behavior and properties of matter. Now, let's move on to slide 19, which covers the interconversion of the three states of matter. This is a fundamental concept because it shows how matter can change from one state to another under different conditions. For example, when we add heat to a solid, it melts into a liquid, and if we keep heating it, it becomes a gas through vaporization. Conversely, cooling a gas can turn it back into a liquid, and further cooling can freeze that liquid into a solid. These processes, melting, freezing, vaporization, condensation, sublimation, and deposition, are all ways that matter transitions between solid, liquid, and gas. Understanding these interconversions helps us grasp how matter behaves in different environments and is key to many practical applications, from cooking to industrial processes. Remember, temperature and pressure are the main factors that influence these changes, making this a dynamic and fascinating aspect of chemistry. Let's talk about how the three states of matter can change from one to another. When we increase pressure and decrease temperature, or alternatively, decrease pressure and increase temperature, these changes can cause matter to shift between solid, liquid, and gas. Essentially, by adjusting these conditions, we can control the state of a substance. This concept is central to understanding phase transitions and how matter behaves under different environmental factors. It connects directly to the broader theme of how matter responds to changes in its surroundings, which is fundamental in fields like chemistry, physics, and even engineering. All right, let's talk about evaporation. Evaporation is a key part of the water cycle, and it's the process where water changes from its liquid form into vapor. This happens mainly when the sun heats up water in rivers, lakes, or even the soil. The heat provides energy to the water molecules, allowing them to break free from the surface and become vapor. One important point to remember is that evaporation is a cooling process. When water evaporates, it helps to cool down the surroundings. It's also affected by factors like temperature, humidity, wind, and surface area. For example, on a hot, dry, and windy day, evaporation happens much faster. This process is essential because it helps transfer water from the earth to the atmosphere, maintaining the balance in the water cycle. Understanding evaporation helps us see how water moves through our environment and why weather patterns, climate, and even our daily water usage are interconnected. Evaporation is a fascinating process where a liquid turns into vapor without actually reaching its boiling point. It's not just about heating up until the liquid boils. Instead, it happens at the surface of the liquid, even at temperatures below boiling. At any given temperature, some particles at the surface, especially those with higher kinetic energy, manage to break free from the attractive forces holding them in the liquid. These particles then escape into the air as vapor. This process is important because it explains everyday phenomena like wet clothes drying. When you hang clothes out to dry, the water molecules evaporate into the air, even if the temperature isn't high enough to boil water. So the key idea here is that evaporation involves only a small fraction of particles at the surface gaining enough energy to escape, which can happen at any temperature. This is part of the broader theme of how matter changes state, and it highlights that phase changes aren't always about reaching boiling points. Sometimes they happen gradually, at the surface, through evaporation. Let's talk about the factors that affect the rate of evaporation. First, increasing the surface area actually speeds up evaporation. Think of it like spreading out water. More surface means more opportunity for molecules to escape into the air. Next, a decrease in humidity, or the amount of moisture in the air, also makes evaporation happen faster because the air can absorb more water vapor. Then, there's temperature. When it gets warmer, molecules move quicker, so evaporation increases. Finally, wind speed plays a role too. Faster winds remove vapor from the surface more quickly, helping the process along. All these factors are interconnected and help us understand how evaporation varies in different environments. So, how does evaporation actually cause cooling? Well, when a liquid evaporates, its particles need to absorb energy to change from liquid to vapor. They take this energy from the surrounding environment, which means the surroundings lose heat. And as a result, the environment around the evaporating liquid becomes cooler. For example, if you pour some acetone on your palm, you'll notice it feels cool. That's because the acetone evaporates quickly, pulling heat away from your skin. Similarly, sprinkling water on the roof or on open ground helps to cool down hot surfaces. The water evaporates, absorbing heat from the surface, which helps to lower the temperature. So, in essence, evaporation acts as a natural cooling process, thanks to the energy exchange between the liquid particles and their surroundings. It's a simple yet effective way to reduce heat in various situations. Water droplets on cold glass. So, what's really happening here? Well, the water vapor in the air is actually surrounding the glass. When this vapor comes into contact with the cold surface of the glass, it starts to lose energy. As it loses energy, it changes from a gas into a liquid. That's what we see as those tiny water droplets gathering on the glass. This process is a perfect example of condensation, which is a key concept in understanding how water changes states. It also ties back to the overall theme of how temperature and energy transfer affect water in different forms. And with that, we come to the end of our presentation. Thank you so much for your attention.